Good morning, students. Myself, Vijay Shankar from Electronics and Communication Engineering Department, Chevrolet Engineering College. Today, we are going to discuss about the sampling theorem, the reconstructed or the recovery sampling, recover of the original signal from. See, we already discussed about what is the communication, digital communication, and what is this statement of the sampling theorem, and how we are combining the original signal x of t and the impulse train delta t minus n into ts. The continuous time signal is converted into the discrete time signal, and combining of these two equations, the modulation x delta of t is equal to sum of n is equal to minus infinite to infinite delta of t minus n into ts x of n into ts. Applying the inverse Fourier, not the inverse, applying the Fourier transformation by using a trigonometric Fourier series, we got x delta of f is equal to fs, sum of n is equal to minus infinite to infinite, x of f minus n into fs. Okay, and in this equation, if x of t would not have been sampled, then there would be only one spectrum x of f around f is equal to 0. See, there is no any values in the periodic function when n is equal to 0. When n is equal to 0 here, fs into x of f. So without any sampling, we have only the x delta of f is equal to fs into x of f. Okay, you see here is like after expansion, x delta of f is equal to fs into x of f plus sum of n is equal to minus infinite to infinite, n not equal to 0 here. N not equal to 0 means n is equal to 0, fs into x of f. So fs into x of f minus n into fs is a periodic signal. Okay. So in this equation, the first term represents the spectrum that would have been obtained without sampling, and the rest of terms under the summation represents the spectrums repeating at multiple frequencies of sampling frequency fs. Okay, my dear friends. Now, if we take the Fourier transformation of the signal x of t, the definition, the integral minus infinite to infinite x of t e power minus j 2 pi f into t. Now, if I am taking the Fourier transformation of x delta of t, the signal here, x delta of t, sum of n is equal to minus infinite to infinite x of n into ts e power minus j 2 pi f n into ts, where the t is equal to n into ts here. This equation we call it as a discrete Fourier transformation. In the above equation, t is replaced by the n into t, n into ts. And how we can recover this function? The sampling frequency is equal to 2 omega, or the sampling frequency is greater than the 2 omega. Okay. So we can recover or reconstruct the original signal. The sampling frequency f is greater than or equal to 2 fm, where fm is a maximum frequency and fs is a sampling frequency. Is also we call it as a fs is greater than or equal to 2 omega, and the omega is called as a maximum frequency. Okay, x delta of f, we know this equation, fs into x of f plus sum of n is equal to minus infinite to infinite, n not equal to 0, fs into x of n minus f minus n into fs. Okay. The last class up to this will be completed, and also the cases we take. The case 1 is greater than 2 fm, and case 2 is equal to 2 fm, and the less than the 2 fm also. Nothing but we are calling it as a aliasing effect. Okay, my dear friends. Now see here, the x of f is equal to 1 by s fs into x delta of f. How in this equation the x delta of f is equal to fs into x of f. So I'm taking the fs x of f is equal to x delta of f minus, bring this in the summation, the left hand side is a minus, and x of f having the multiplication factor of a sampling frequency. Now it is a 1 by fs x delta of f minus the sum of n is equal to minus infinite to infinite and not equal to 0 also. And here the fs is cancelled, x of f minus n into fs, where the fs is at 2 omega is equal to. Here I am taking the above equation will be fs is equal to 2 omega. See, the figure whatever you are showing here in the below is a figure actually a reconstruction function. Shows the sampled version of a signal x delta of t, shows the sync pulses of varying amplitude located at the sampling instance. The peaks of the sync pulses, represents the amplitudes of the sample. This signal is given by the equation is x plus or minus 2ts sync to the 2 omega into 2 plus or minus 2 ts plus and so on. Okay, after expanding this equation in terms of the sync function, the signal is given by the equation here can be passed through low pass, through a low pass reconstruction filter to get a smooth x of t. Here we have assumed that the minimum sampling frequency should be equal to 2 omega. That is twice of maximum sampling frequency. Twice of the maximum sampling frequency, or the omega is equal to maximum sampling frequency. Statement of sampling theorem is proved here that a signal can be completely represented. And recovered from its samples if sampling frequency is twice the maximum signal frequency, fs is greater than or equal to 2 omega. So until this, yesterday we discussed. Here, observe one signal I take is a minus omega to the omega, nothing but a minus fm to fm. Okay, this is equal condition. Equal condition means exactly at the minus omega, it starts the fs value, 2 fs value, and so on. Okay, and here the minus fs and the minus 2 fs, where n is equal to 0 here, and n is equal to 1, and n is equal to 2 function, my dear students. Okay. And this is a reconstructed filter by using the sync functions. Sync function we already know. The sync function varies maximum value and it goes to the 0. Again, it decreases the amplitude and goes to the 0 like this. The sync function. Okay, my dear students. Gradually, it decreases the amplitude also. This is a sync function. See here the sync function. The 2 times we'll get to here, and these also like this. Slowly it decreases. At ts and 2 ts to 3 ts, the original signal what we have, x of t signal, it is reconstructed. The sampled version of the signal x of t and the reconstruction of the x of t from its samples. Okay, my dear friends. Now, aliasing also we already discussed. Aliasing. This aliasing is sampling theorem. We assumed that the signal x of t is strictly band limited. The statement what we are already know. However, in practice, an information signal can contain wide range of frequencies and cannot be strictly band limited. Therefore, the maximum frequency omega in the signal x of t cannot be predictable, as it is not possible to select a suitable sampling frequency fs. The sampling theorem states that fs is greater than or equal to 2 omega. Let us see that two conditions such that the sampling frequency is selected to be less than the 2 omega, less than the 2 omega, is equal to 2 omega. By using the ideal low pass filter, we reconstructed the signal, what we assumed. But now we can assume the fs is less than the 2 fm. Actually, it is omega is nothing but fm only. Okay, my dear students. What happens when it is a less than the 2 omega? Yesterday I explained. If I am taking here a signal with minus and 0 and 5 is the actual signal when n is equal to fm at 2 omega, less than the 2 omega. Now I am assuming the fm is a 5 here. Okay, is a minus fm and plus fm. What is the condition we are taking here? Fs is less than the 2 fm. Fs is less than the 2 fm means Fs is less than the 2 into 5 is a 10 here. Now I am assuming the Fs is a 8. Okay, 8. So that whenever I am taking the minus 5 to 5, when n is equal to 0 here, the periodic function will get it's a 5 here, and the peak value will get at the 8. Okay, these are Fs. Now, what is it before here? The 5 minus 5, 0 minus 5 here, and 5 minus 0, it is a 0 here. 8 minus 5. 8 minus 5 means it is a 3. It starts at the 3 and not up to that. It starts at the 3 here and n is equal to 0. Now this value is 8. 8, 3 and 8 plus 5 here. What is 8 plus 5? The 13. Okay. Now this value is 8 and here the n is equal to 1. This n is equal to 1 and this also the n is equal to 0. Minus 8, minus 3 and minus 13. The difference is here the minus 13 to 3 is a 10 only. And also minus 5 to 5 is a maximum frequency. Minus 5 to 5 is a 10. So now it is a overlap here. See the overlap function. Overlap, low frequency shows in the high frequency and high frequency shows in the low frequency, my dear students. See, shows an effect taking the sampling rate less than twice of the maximum sampling frequency. The spectrum of sample signal consists of spectrums repeated at plus or minus, repeated at the plus or minus n into Fs, as can be seen in this here. Each spectrum extends to omega hertz around the sampling frequency. Around the sampling frequency. Whatever here the dark shaded, we are saying that aliasing effect. Aliasing effect. Whenever if we take the condition is Fs is less than the 2 omega. 2 omega. Maximum frequency, the sampling frequency is less than. Okay. the W is, say, FM, 2FM is greater than the FS, or FS is less than the 2FM. Both are the same, my dear students. Here the C, they are saying that the FS is less than 2 omega, or omega is Fs by 2. The spectrum interference with each other, this is called aliasing. Okay, this is called aliasing. Because of aliasing, high frequency component in the spectrum of a signal takes identity of a low frequency in the spectrum of its sampled version. Means high frequency is appears at the low frequency, and the low frequency appears at the high frequency ones. The signal x1 of t actually has higher frequency f1, but it is sampled at a low rate. Fs is less than the 2 omega. This is one of the example. What I show, taken it is a -5 to 5 like that. Okay. Now, the aliasing occurs in the sampling process, and the high frequency components are covered to low frequency. Therefore, because of aliasing, the signal is not represented properly. The signal is not represented properly with all its contents in its sampled version. Therefore, the sampling theorem needs to be satisfied when Fs less than 2FM or the less than 2 omega, it is not satisfied because of the aliasing effect. What is aliasing effect? Is nothing but high frequency components are converted to the low frequencies. Therefore, because of aliasing, the signal is not represented properly with all its contents in the sample version. Okay, my dear students. And the Fs is greater than the 2 omega. Here also greater than the 2 omega, we are using the low pass filter. Either you can use the ideal low pass or filter, or it is a practical low pass filter to recover the frequency. In this, the two formulas we are using the Nyquist interval 1 by 2FM or the 2 omega. Nyquist rate is equal to 2 omega. Nyquist rate, when the sampling rate becomes exactly equal to the 2 omega samples per second for a signal bandwidth of omega hertz, then it is called Nyquist rate. When the sampling rate becomes exactly equal to the 2 omega samples per second for a signal bandwidth of omega hertz, then it is called Nyquist rate. The Nyquist interval is obtained as 1 by 2 omega seconds. Nyquist rate is at 2 omega hertz, and Nyquist interval is a 1 by 2 omega seconds. Okay, so both are, it is a frequency and this one is a time, inversely proportional. Nyquist rate is frequency, Nyquist interval is a seconds, the time, inversely proportional. One, it is a 2 omega means that is a 1 by 2 omega. Okay, my dear friends. See the low pass filter interpolation. Yesterday I already explained this one. There is a God band is there, God band, omega FM here, Fs minus omega and Fs plus omega. Fs is the value, so greater than if I am taking the 15. So like once again I will explain this with the diagrams. So I taken is a triangle wave with the -5 and 5. What is a -5 and 5 is a FM or omega minus FM. And here the FM. Okay, my dear students. Now, the periodic signal with the God band is a greater than. We are taking the greater than value. See, Fs is a greater than the 2 omega. Or the Fs is a greater than 2 FM. Okay, what is a FM? I assume the 2 into 5. So, Fs is greater than the 10. Fs is greater than 10. So I assume the Fs is equal to 15. Let us is a 15. Okay. Now taken, it is a minus Fm and the plus Fm, 0. Add the 15, it is a Fs. Okay, my dear student, Fs. Now, what is this value? Fs minus omega, and this one is a Fs plus omega. Minus omega. Fs, what is the Fs? I assume 15. Minus, what is the Fm here? Fm is a 5. Fm is a 5. 15 minus 5, the value is a 10 here. This is a 5, 0, minus 5. And this one is a value is a 10. What is the Fs? 15. This is a Fs value, 15. And Fs plus omega. Fs plus omega means Fs I assume the 15. And Fm is a 5. So Fs plus 15 is a 20. Okay, this is at n is equal to 1. And similarly, in the left hand side also, the left hand side, if I am taking, what is the value here? This is Fs minus Fs. And this function, see the minus Fs plus omega. Minus Fs plus omega. And minus Fs minus omega. What is a minus Fs? Minus 15. Minus Fs omega. Minus Fs 15. Plus omega. What is the omega? Nothing but Fm only. 5. Minus 15 plus 5 is a minus 10. So this value is a minus 10. So this is a minus 15. So minus Fs minus omega. Minus Fs minus omega. 15 minus minus 15 minus 5 is a minus 10, 20. What it matters, friends? Now there is a gap is occurs when we are assuming that the Fs is greater than the 2m. The Reconstruction filter, the low pass filter or interpolation filter. Okay, my dear students. So using this low pass filter, see I will use another one. Okay, ideal low pass filter or practical low pass filter, we can recover. It is not allows a high frequency here, it is not allows the low frequencies. In between of the frequencies only it is allows and is reconstructed. What the original signal I taken. Okay, my dear students. This example yesterday I already explained. Or if we suppose, if we take is equal to Fm. Is equal to Fm means Fs is equal to 2Fm. What is the Fm? I assume here the 5. So Fs is equal to 2 into 5. That is a 10. So Fs is also, I am taking the 10 now. Okay, my dear friends. Now the Fs is at 10 means, for example, if I take here, okay, students, the second condition, Fs is equal to 2Fm. Already we've seen that it is Fs is greater than 2Fm. Now we can go for the Fs is equal to 2Fm. Now I'm assuming Fs value, Fm value is minus 5 and 0 and 5. The 5 is Fm. So 2 into Fm, that is a 5, is equal to 10. So Fs is also, I'm assuming now is a 10 ohm. Fs here, the value whatever we have, that is a Fs 0. The value of Fs is at 0, not the 0, it is a 10, my dear students here. And this value is a Fs minus Fm. And this value is a Fs plus Fm. Okay. Or we can say it is a Fs plus or minus Fm. Fs is equal to plus or minus EFM. Okay. Now similarly, this is a periodic signal minus FSM minus Fs. What is a minus Fs? Fs is a 10, so it is a 10 value. At n is equal to minus 1. N is equal to minus 1 and n is equal to 1 here. N is equal to 1 and this one is n is equal to 0. In which equation we are substituting these values? X delta of F is equal to Fs sum of n is equal to minus infinite to infinite x of F minus n into Fs. Okay, my dear students. For n is equal to 0, x delta of F is equal to Fs into x of F. Okay, and here the FM heads in this condition. Now, if I am taking the n is equal to 1, x delta of F is equal to Fs x of F minus Fs. F minus Fs. Okay. In this case, it is a Fs plus or minus Fm. So see here the Fs minus Fm and Fs plus Fm. That is a Fs plus or minus Fm value when n is equal to 1. So it's a minus Fs is a minus 10 means and this function is a minus Fs plus Fm. Okay, my dear students. Minus Fs plus Fm and this value is minus Fs minus Fm. So see the minus Fs is a minus 10, minus Fm is a minus 5. So this value is a minus 15 as we assume. Minus Fs is a minus 10 and here see the minus Fs plus Fm. Minus Fs is a minus 10 plus Fm is a 5. So minus 5. Got it, my dear students? Okay, but here there is no any guard band and this condition will get for the Fs is greater than F to Fm. And this case there is a gap is there in between of a waveform of minus omega to the omega or minus Fm to the Fm values. Now whenever if we are assuming this condition, the second condition, what we are saying Fs is equal to 2Fm, there is no any gap between of the waveforms n is equal to 0 and n is equal to 1. Here we are using a practical low pass filter. Using the practical low pass filter, there is a high frequency will get in the inside. So now to recover the original signal from this after the sampling, to recover the original signal from this, have to use an ideal low pass filter only. An ideal low pass filter. See, ideal low pass filter exactly will get like this. It removes the higher frequencies and it allows only the low frequency value. And here we are not using the practical low pass filter. For Fs is greater than Fm, using practical low pass filter to recover the original signal. See here there is a practical low pass filter. Slowly it is increasing and decreasing like this. And for Fs is equal to 2Fm, using the ideal low pass filter you are using to reconstruct the filter. So both are the low pass filters only. Even here we can use ideal low pass filter also, but we are using the practical low pass filter to get there is a guard band is there in between, so you can use a practical low pass filter here, and here itself have to use only the ideal characteristics only to recover the original signal from after the sampling. Understood, my dear students? These two cases, what we have said that the sampling definition is satisfied. What is the sampling definition? I already told that a signal which is band limited to the FM heads a signal which is a band limited to FM hertz. Nothing but here the minus 5. I assume the values only, my students. Actually, this value is a FM and this value is a minus FM. A signal which is band limited to FM hertz can be completely recovered from its samples. If the samples are taken at the rate of Fs is greater than or equal to 2 FM. Once again, I'm saying that it is a sampling theorem statement. A signal which is band limited to the maximum frequency FM hertz can be completely recovered from its samples. It is completely recovered from its samples if the samples are taken at the rate of Fs is greater than or equal to 2 FM. The first condition we already seen, the greater than the 2 FM, there is a God band is occurred. Okay, mine FM and the FM, it is Fs minus FM, my Fs plus F. And here the minus Fs plus FM, minus Fs and minus FM. Okay, my dear students. Assuming that it is a FM is equal to 5, then Fs is equal to 10 whenever it is equal, and Fs is equal to 15 when it is a greater than. In the third condition, you can go for, it is only the recovered with this condition only, my dear students. Either it is a greater than or equal to. For greater than, we are using a low pass filter of practical characteristics, and equal to, we are using a ideal characteristics to recover the original signal. Understood? Then coming to the last one. Fs is equal to 2, not is equal to, less than 2 FM. Less than 2 FM. We already seen that. Less than the 2 FM is there is a overlapping occurs. That is nothing but aliasing. Nothing but it is a aliasing. See here, when Fs is less than the 2 omega, less than the 2 omega means there is a higher frequencies inside the low frequency, and low frequency is there in the higher frequency. So the maximum frequency omega at the signal cannot be predictable actually. It is not suitable to select the suitable frequency Fs, and sampling theorem states that Fs is greater than or equal to 2 omega 1. Let us also see in the two conditions such that the sampling frequency is selected to be the less than the 2 omega and greater than the 2 omega. And in the less than the 2 omega, there is a overlapping occurs, nothing but aliasing. Okay, let us see. If I use a waveform, the same thing, I am taking the same example what we taken in the greater than and the less than, plus 5, 0 and minus 5. Nothing but is a FM minus FM. Is a band limited to the FM hertz when n is equal to 0. Now I am assuming that FM is equal to 5 means 2 into 5 EFS. EFS is less than the 10. Okay, now you can assume that less than the 10 value, so Fs is equal to 8. Let. Okay, the 8 value is less than the 10. Fs is less than the 10 means let us here Fs you can assume that n is equal to 1. Now what is the value before that? There is a difference of 5 in between 8. Definitely the value what we have is a difference is a 5. Okay, my dear students. So 8 minus 3 and this value is Fs minus Fm. Fs is minus Fm, and this value is a Fs plus Fm. Fs plus Fm. What is the Fs here? 8. 8 minus, what is the Fm? 5. And here Fs plus Fm. What is the Ff here? Fs here 8 plus, what is the Fm? 5. So 8 minus 5 is a 3. And here the 8. There is a difference between that 8 and the 3 is a 5. Okay. Now Fs plus Fm is equal to 8 plus 5. 8 plus 5 is 13. So difference is 8 and 13 is a 5. Following my students. Now there is a overlapping is occurs here. Okay, there is a overlapping here. Means high frequency whatever we have, that is shows in the low frequency value, and the low frequency that is inside the high frequency. Okay, so see here, the omega is nothing but what I assume here, the Fm, and this one is a Fs minus Fm. Fs minus Fm, and this value is Fs plus Fm. Okay, and so on, the 2 Fs and 3 Fs, and when n is equal to 2 and n is equal to 3, that becomes of x of F minus n into Fs. And this n values varies. When n is equal to 1, this value is F minus Fs. Okay. Similarly, in the left hand side also, minus Fs. What is the Fs? I assume minus 8. It is internally it is a overlap here. And this point is minus Fs plus Fm. What is a minus Fs? Minus Fs is 8, Fm is a 5. Minus 8 minus 5 is a minus 3. So minus 8 minus 3 means difference is a 5. And here minus Fs minus Fm. Here it is a one time, it is a plus, and one time the minus. Minus 8 minus 5. So minus 13. So here also there is a overlapping occurs. You see there is a overlapping occurs. Following my dear students. In this case, if you use either it is a practical low pass filter, either you can use a ideal low pass filter, we can't recover the original signal. We can't recover the original signal because of there is a aliasing occurs. After the filter, it shows like this. Okay. There is a gap here. There is a distortion occurs because of aliasing. There is a distortion here. What we are seeing, there is a distortion. Only up to this value only it is recovered. But the point where we are, it is a overlapping occurs is there, that is not recovered. Understood, my dear students? So it is band limited to FM heads. It is fully recovered or completely recovered by its samples if the sample rate is FFs is less than, greater than or equal to FM only. When it is a less than FM, it is not recovered. It is not recovered because of aliasing. Understood, my dear students? Because of the aliasing occurs. Or in the examination point of view, how we can avoid the aliasing? How we can avoid the aliasing means we can take the Fs is greater than or equal to Fm1. If any occurs here, after the sampling, aliasing occurs, how we can recover? How we can rectify that one means by using the Fs is greater than or equal to Fm only. Understood? Different ways to avoid the aliasing. Different ways. One is Fs is greater than the 2Fm. There is a God band occurs, and Fs is equal to 2Fm. What is aliasing means? So the definition of aliasing is when the high frequency interferes. When the high frequency interferes with the low frequency and appears as low frequency and appears as low frequency, then the phenomena is called aliasing. Understood, my dear students? What is aliasing means? See, the spectrum interfere with each other. This is called aliasing. Because of aliasing, high frequency component in the spectrum of signal takes identity of a low frequency in the spectrum of its sampled version. Understood, my dear students? Another way, there is a definition is there here. The spectrum interfere with each other. This is called aliasing. Because of aliasing, high frequency component in the spectrum. See here, this is a high frequency component in the spectrum of the signal takes identity to low frequency in the spectrum. Low frequency in the spectrum of its sampled version. Understood, my dear students? Otherwise, when the high frequency interferes with a low frequency and appears as a low frequency. See, this is a high frequency signal, interferes with a low frequency signal and appears as a low frequency. This value what we are showing here, see, I am showing here, this is a high frequency. When the high frequency interferes with a low frequency and appears as a low frequency, then that phenomena is called the aliasing. And what is the different ways to avoid this aliasing? By taking off Fs is greater than 2fm or Fs is greater than is equal to 2fm. The two ways we can avoid the aliasing. Understood, my dear students? Okay. This is a very, very important the reconstruction of the sampling by using the low pass filter. Okay, the signal x1 of t actually has higher frequency fn, but it is sampled at lower rate. That is, fs is less than the 2 omega. When the samples are reconstructed, we get the signal x2 of t, which is of low frequency f2. This happens because of aliasing. Because of aliasing. This shows high frequency signal takes an identity to the low frequency because of aliasing. Understood, my dear students? The other way, the definition, or we can simply define the aliasing means up to this. The spectrum interfere with each other. This is called aliasing because of aliasing high frequency component in the spectrum of the signal takes identity of low frequency in the spectrum of its sample. Following, my dear students, three conditions. Fs is less than the 2fm, getting aliasing effect. And to avoid this aliasing, we are going to two different techniques. That is, Fs is greater than the 2fm, or another way, the Fs is 2 is equal to 2fm. Understood? Now the next topic is, we go for the next topic. There is two sampling techniques, different types of the sampling techniques. So one is impulse, and next one is impulse sampling, and the second one is natural sampling, and third one is flat top sampling. Okay, now let us see that one. types of samplings, my dear students. The first of all is the types of sampling is an impulse sampling. We already seen that the impulse sampling, how we can sampling the signal x of t with the delta of function. X of t is the original sampling as a sinusoidal function, and the impulse signal is an impulse train. All the impulse signal can add the sum of n is equal to minus infinite to infinite delta of t minus n into ts. That is a delta t of t. Okay, my dear students. And now we are combining these two to get it is a x of n into ts. That is x delta of t is equal to x of t, x delta ts or delta ts of t. So x delta of t is equal to, combining that, the sum of n is equal to minus infinite to infinite x of n into ts and delta t minus n into ts. That is a sampling time, my dear students. Here that is representing that is a t on. Nothing is a difference. See here the sampling frequency fs is equal to 1 by t. Or we can represent 1 by ts also. Nothing is a difference. Is a ts and n into ts. We already seen this is the equation we already derived in the sampling introduction and the sampling theorem. And now we can apply the Fourier transformation on both sides. Before that, it is a Fourier transformation on both sides. We taken that is a delta of t function by trigonometric Fourier series. Trigonometric Fourier series, that is x delta of t is equal to, we got a fs into sum of n is equal to minus infinite to infinite x f minus n into fs. We already derived this equation. This is also f, my dear students. X delta of f is equal to. So after applying the Fourier transformation, in the left hand side x delta of t is a Fourier transformation of x delta of f is equal to the Fourier transformation of the two functions, and there is a signal and we have only the Fourier transformation to can apply that is x of t here. It is a n into ts. There is no any t function, the t. So with respect to the t function in the left hand side and the right hand side, the Fourier transformation of delta of t minus n into ts. The t minus n into ts. It is a Fourier transformation of e power minus j omega t. E power minus j omega t. Any function is a delta of t minus n into ts is a 1. Here you can, it's a 1 into e power minus j omega t. The value is a 1. And if it is a shifted value, the delta of t minus 1 into t, e power minus j omega t, that is also the value is a 1 at t is equal, n is equal to 1 function. And so on, you can apply, we'll get the exponential value only, e power minus j omega n into ts. N into ts. When here the 1, 2 and so on, it is taken off denominator 1 by ts. 1 by ts. Omega is nothing but here I am taking the m value. So finally you can apply that it is a e power minus j x delta of t is a x of f. What we here wrote, taking that is a Fourier transformation of delta t minus n into t is e power minus j omega n into ts. And it is a sum of, you can take that. The sum of you can take 1 by ts e power minus e power, not the e power, sum of n is equal to minus infinite to infinite e power j m omega naught t. Following, my dear students. Now, see, after finally we got the Fourier transformation is 1 by t, nothing but 1 by fs, and x of f minus n into ts. What I wrote here, the function x delta of f is equal to efs, the sum of n is equal to minus infinite to infinite x of f minus n into fs. Fs here the 1 by t because of the inversely proportional to the time and the frequency, and sum of n is equal to minus infinite to infinite when this becomes of f minus n into fs, and fs is a 1 by t, 1 by t, and we are changing that frequency in the omega, the 2 pi values. We can add the 2 pi here, 2 pi by t, nothing but the omega only. Okay, omega. That is the frequency you can take. Here it is omega there. Understood, my students? So, when I am taking the original signal with equal to function, fs is equal to 2fm. By using the ideal low pass filter, we can recover. And this condition is overlapped when we can take it as a fs is less than the 2fm. So we already seen this, the impulse sampling technique. The impulse sampling technique, but it is in the practically it is not possible by using the impulse technique. Impulse sampling is also called as an ideal sampling, or is also called as an instantaneous sampling. So 3 names is there. We can also call it as impulse sampling, or we can also call it as ideal sampling, or we can also call it as a instantaneous sampling. Following my students, instantaneous sampling with this function only. Okay, but it is not applicable for the practical functions, and here the noise is also more. When you are using the sampling with the impulse sampling or instantaneous sampling, the noise is also more here. To avoid that, we are going for the another sampling technique. That is nothing but natural sampling. Following my students, natural sampling. That is the second one, second type of sampling. Natural sampling, you can also call it as a chopper sampling. Natural sampling or the chopper sampling. This is similar to that of the impulse sampling only. In natural sampling, the pulse has a finite width. You see here, actually, in the previous case, the width of the sampling is 0. Here the delta of t, and this function is the delta of t minus ts, and this sample is a delta of t minus n into, not the n, it is 2 into ts and so on. And here the width of the sample is 0. The tau is equal to 0. But here there is a tau is there, a finite. Okay, my dear student. And I'm taking the full cycle, that is a ts. The total it is a ts. And this width of this sample is a tau. Fine. And here the tau is a 0. In the previous case. In the previous case, the width of the tau is a 0. But in the natural sampling, the pulse has a finite width tau. It is also called as a chopper sampling because the waveform of the sampled signal appears to be chopped off from the original signal waveform. From the original signal waveform. Let x of t be the analog continuous time signal that has to be sampled at a rate of fsh. Okay, whenever there is a switching on, we can give the x of t signal, and it is getting of the x of t with chopper sampling, having a width of the tau. So when c of t goes high, a switch S is closed. When it is a 1, the S is closed. Means S of t is equal to the x of t will get. X of t is equal to x of t, and it having the amplitude what we have in the sampling signal, amplitude is a. So whenever it is a switch is open means the C of t is equal to 0. C of t is equal to 0, my dear students. Whenever it is a 0, And S of t, what will get the S of t is a 0, because there is no any signal will get in the output side, the 0. So by using these two functions, we can write as x of t is equal to c of t into x of t. C of t into x of t. So what is the x of t here? The sum of n is equal to minus infinite to infinite x of n e power j n omega naught t. This is according to the exponential Fourier series synthesis equation, saying that x of t is equal to sum of n is equal to minus infinite to infinite x of n into e power j n omega naught t. And x of t is equal to sum of n is equal to minus infinite to infinite x of n e power j, and omega naught I am writing it as 2 pi by t naught, or 2 pi f naught actually. Okay, the periodic pulse train of c of t, t naught is equal to ts, or it is a 1 by fs. Okay, my dear students. So I taken here the function is an exponential function and is a synthesis equation. Synthesis equation. Analysis equation means the exponential is a negative value, my dear students. Exponential value is a negative value. Understood? That is a c of t actually. To get it is a c of t values. So in this equation, the 1 by t naught, or you can call it as a 1 by ts. Okay. Now, the equation will be the x of t is equal to c of t. Whenever this switch is on, c of t is equal to sum of n is equal to minus infinite to infinite cn e power 2 pi n into t fs. Okay. And if it is a rectangle function, rectangular pulse, the cn is expressed. We already seen that it is a sinc function we'll get. Sinc function. After expanding that, it is a c of t is equal to get it is a c of n as a coefficient of the c of n. The t by the t naught into a, the sinc fn into t, or fn is r, can also written as n into fs, the harmonic frequency. The t is a pulse width, nothing but is a tau. Therefore, the c of t is equal to sum of n is equal to minus infinite to infinite. You can substitute that ctn. Cn is a ta by ts. Sinc fn into t, or it is nothing but the tau e power minus j 2 pi fs into n into t. Okay, my dear students. How we get this equation? We already take the one example, the rectangular pulse train. Rectangular pulse train. I will show that also, my dear students. A rectangular pulse train. We already did that one. See, this is the rectangular pulse. The rectangular pulse is defined as from a vector of t by t, the a is equal to minus t by the t by 2. After taking that is a Fourier transformation, we'll get a into t sinc f into t, my dear students. A into t sinc f into t. Here I am taking that it is a t value, the tau, and the 1 by ts. Using this function, I substitute there ta by the t naught and sinc f into t naught. Actually, here it is a pi into a, pi into f, not the pi into a, the pi into a. By using this rectangular pulse, we already derived this expression. We already solved this problem, and this as taken as a x of cn is the value. The cn is equal to, okay, we're substituting in the c of t. You see the TA by the T naught and the sink F into T, where Fn is a N into Fs. Substitute this Cn value in this equation. The C of T is equal to sum of N is equal to minus infinite to infinite. TA by Ts sink Fn into tau, and already we have the e power minus j 2 pi Fs into N. 2 pi Fs is nothing but e power j omega naught N into T. Actually, it is a k into T in the Fourier series. I taken it the N is equal to minus infinite to infinite. Okay, and this C of T can substitute in the X of T, S of T. S of T is equal to the combination of C of T into X of T. So what is the C of T? The total function here is the C of T into X of T. Represents the natural sample signals. And Fourier transformation of X of T is obtained that S of F as S of T. The Fourier transformation of the S of T. What is the Fourier transformation? These are tau A by the Ts, sum of N is equal to sink F tau. The Fourier transformation only for the T functions. X of T into e power minus j, not the minus is a plus, e power j 2 pi Fs N into T. It's a shifted operation. How much it is? Actually, the 2 pi Fs is nothing but omega, my dear students. E power j omega s N into T X of T. So apply the Fourier transformation of this function. Omega s N is a subtraction value. Actually, the X of T into e power j k naught into T. What is the Fourier transformation here? X of omega minus, that is the omega naught, x minus omega. Instead of omega naught, here the omega s into N. So x of F minus Fs into N. Okay, I'm taking the 2 pi as a shortcut notation. So the Fourier transformation by using the shifting property, x of F minus Fs. So S of F is equal to tau A by the Ts, sum of N is equal to minus infinite to infinite. Sink function with x of F minus Fs into N. So actually, the x delta of F is equal to Fs into sum of N is equal to minus infinite to infinite x of F minus N into Fs by using the sampling or instantaneous sampling or the ideal sampling. We got this function. Now, instead of that is a x of F, nothing but x delta of F only, my students. The tau A by Ts, nothing but Fs. The sum of N is equal to minus infinite to infinite. The same function what we got the N into Fs, but it is having some sink function also. Sink Fn into tau. Okay, Fn into tau. Nothing but the spectrum of a natural sample. See here, there is a gap is there. Now we got the gap. In this condition, there is no any gap. It is a overlapping occurs. But here there is a now by using this sink function, there is some gap we got here for the Fs, 2Fs, minus Fs, and the minus 2Fs. Okay, here the sampling rate is a Nyquist rate. Understood? Okay, my dear students, in the tomorrow's class, we can see the last one is a very important one, is a flat top sampling. Okay, thank you.